question is, why did we care about diagrammatic algebra in the first place? If they were just about random equations between diagrams, they wouldn't be very useful. I think the reason is that usually string diagrams do sometimes give us an intuition of what we can do or cannot do with them. And this is definitely the case for these examples, which is the one that convinced everyone in the first place. The example of the treatment of the theory of adjunctions by string diagrams, so the snake equations. And this immediately gives us a way to compose these things to form something like the pair of pens monad, which kind of gives a nice geometric topological intuition about the theory of monoids, or even the theory of Frobenius algebras if we also have the flipped upside down version. And so having an intuitive explanation of Frobenius algebras already gives us a nice intuition for the part of the ZX calculus which relates to spider loads. But the other big equation of the ZX calculus, the bialgebra equation, does not really have such a nice topological explanation, at least at first sight. Like these two diagrams are very different. I don't know, one has loops, one doesn't. Or the copy diagrams are even worse, because on one side there is a disconnected diagram and on the other side there's a connected one. So something that I wanted to do is to find an equally nice topological explanation for this law and similar laws. And that's what I'm going to give you, but first I have to take a detour. So I think another convincing use of string diagrams has been done by Jamie Vickery in his bicategorical treatment of the teleportation protocol. And the specifics don't really matter here, but the point is that the geometric intuition of this law is that one has this cup-shaped diagram, and one can kind of slide it through this wire going from down to up. And this describes teleportation protocols in a very general setting. And in fact, this kind of sliding behavior appears in a lot of equations for the use of string diagrams in two categories, which have been catalogued by Dan Marsden and Ralph Hintze in a very nice paper. And this is another case of sliding equations in which we have something like a monoid multiplication which we slide through this other wire. And this turns out to describe precisely the notion of homomorphism of monoids for instance, of homomorphism of monads, for instance, in the two categories, and which also encompasses the notion of homomorphism of monoids. But still, it is not clear why this kind of sliding behavior appears to be correlated with homomorphisms and other notions of naturality. So I would like to take a different angle at this equation. If we take something like that multiplication cell, and we think of stretching it in space in the third dimension, and then we take something like that kind of white to yellow morphism, and we do the same thing but in an orthogonal direction, and then we put the two together, we have this kind of cube of intersecting surfaces. And if now we look only at the faces of the cube that are visible on the front, we get something like this. Now if we only look at the faces of the cube that are not visible, that are on the back, we get this. And if we now flatten these two triples of faces, we get precisely something that has that shape. So the idea here is that the geometric correlate of naturality, rather than sliding, is orthogonality of cells, and the sliding only comes up when we take these cubical things and we make them into something with one source and one target. And this is the intuition, and I will try to make it more precise. So traditionally, when we define an algebraic theory, we give a bunch of generators and we give some equations, some relations between them. But there is this idea in the field of higher dimensional rewriting that rather than having equations, we should just make equations into generators of a different dimension. So we transform equations into directed things, rewrites or rewrites. And this leads us to higher categories. And in particular, it leads us to this structure known as a computad, or also known as a polygraph in high-dimensional rewriting, where one defines these high-dimensional algebraic theories by progressively adding generators and kind of letting generators be freely composed, and then adding some rewrites on some high-dimensional generators on these compositions. And for instance, a one-dimensional computad is just like a graph. So one gives a zero-dimensional generator and some edges, which are like one-dimensional generators. And if one takes like the category generated by these graphs, this would be the model of natural numbers. But in high dimensions, one could also add a two-dimensional cell going from, for instance, from the point to this interval, and this would now define a different theory. And the point is that giving a presentation of a computad is, in a certain sense, it's very similar to giving a combinatorial description of a cell complex in algebraic topology. Only with the difference that the cells, rather than being just topological objects, have a notion of direction. So the simple idea is that we can take these algebraic theories described like these, and we can compose them as we would compose topological spaces. And the main operation here is something called the Kranz-Gray tensor product, which is an asymmetric tensor product on higher categories, which happens to restrict to these freely generated theories. So freely generated tensor, freely generated is again freely generated. And if we just forget all directions and take some kind of topological realization of this product is just the Cartesian product of topological spaces. And we can also perform different topological operations, such as taking disjoint unions or quotients. And for instance, if we have a computad or directed space which looks like an interval, so just one edge going between 2 points, and we take a presentation of the theory of monoids, which in particular will include some multiplication cell. Then we can tensor them and obtain something which is like interval times something, so it's like a cylinder on a theory. And for instance, if we take interval tensor multiplication cell, we get something which is one-dimensional times two-dimensional, so it's three-dimensional, and it has exactly that shape I showed you before. And the same thing happens if we take, for instance, the unit, which gives us the other kind of sliding equation for homomorphisms of monads. So we can kind of think of revisiting this cube picture and now see it as actually as literally a Cartesian product of a directed square, which is the multiplication square, times a one-dimensional thing, which is that interval thing. And the funny thing is that, well, maps of cylinders into another topological space are just homotopies of maps. So in a certain sense, we get to see homomorphism, the notion of homomorphism of algebras as a directed version of homotopy. However, if we are considering like more strictly speaking algebraic theories, usually one does not have these colors. One just has things which are like props, so there are like monoidal theories. And in that case, these theories are naturally pointed. They have a point which is the one color they have, so it's a single zero cell. So one can consider the pointed operation of topological spaces, such as the smash product, which is a quotient of the Cartesian product, or in this case, the tensor product, in which one eliminates everything which is of the form something from x times the point of y, or the point of x times something from y. And when we work graphically with these mesh products, we would just take the tensor, and then we would basically erase everything from diagrams, because that's what quotienting means graphically, except the intersections of diagrams which come from one of the theories and the other theory. So as an example, we consider this match product of the theory of presentational theory of monoids with itself. And what happens is that, for instance, having multiplication smash multiplication. So we said we take the tensor product in which we would have two like multiplication cells sliding past each other. So we have here the two things in this position. And then we have two ways of sliding them. We either slide first this one, we go from here to here, and then we slide the other one past the first one, or we do the opposite thing. So we first slide the one in the upper left corner, and then the one in the lower left corner. And we can draw these like sliding moves as surface diagrams in three-dimensional space. And if we forget about everything but the intersections, what we have here is, here we have one intersection, which then becomes two intersection, and the same thing about here, one intersection becoming two. And then after this sliding move, they both become, again, they become in different pairs. It goes from two intersections to one intersection. Well, if we do this upper half, we have first two intersections, then it becomes one intersection, but in a different direction, and then it becomes two again. And if we just draw these like intersection diagram in free space, it has exactly the shape of the bialgebra law. And so actually this smash product can be seen as a presentation of the theory of bialgebras. The other bialgebra equations are exactly given as multiplication smash unit or unit smash multiplication. And the other nice thing about here about this is that it's naturally higher dimensional. So for instance, this product will also have all sorts of coherence equations automatically given, such as a coherence between using associativity and then using bialgebra. And so yeah, this is and so I've kind of in this talk I've focused only on this kind of topological intuition about these operations, but actually I think that this approach can lead to a kind of useful imputation of methods from homotopy theory or homology theory to studying these higher-dimensional theories. And I still haven't results about that, but I hope that it can be done. Thank you.
Thank you.
So you took the smash product of monoid with monoid and you got bialgebra, right?
Yeah.
So I would have expected it to be the product of monoid with comonoid.
It's actually it's a bit funny because in this kind of in this approach, basically like the right picture of this product is the cubical picture, and then when one passes from the cubical picture to a globular picture, actually one makes some choices in how to direct things. So in particular, if there is something about odd dimensions which kind of changes the sides. If we chose a different presentation of the theory of monoids, one where, for instance, the multiplication is a 3-cell, and we kind of have, which is what we would do with props in which you already have permutations, so you would go in high dimensions. Then actually bialgebras would be monoids smash comonoids.
Okay. Any other questions? Stefano?
Is there an equivalently pretty characterization of Hopf law? Can you work on that?
Yes, but I don't have a good characterization of Hopf law. I think there might be some fundamental reasons why this is not the case. It has to do with inverses having all sorts of weak versions that multiplication doesn't.
Okay, then let's have tea. And thank you.